Okay, so I'm going to talk to you about GPU offloading on Wayland. So my name is Axel Davy. I'm a student at the École Normale Supérieure of Paris. So first, I will tell you what are the different technologies involved in GPU offloading and how we can handle them. Next, I will explain how GPU offloading is handled with X DRI2 and how it is. Then I will show you how we decided to make it work with Wayland. And to finish, I will tell how it can work with X Wayland. So first, the different technologies involved in GPU offloading. The first technology we can have in mind is rendering. So to render, we have to be authenticated to be able to render. The traditional way to be able to render is there is a master, a DRAM master, for example, the X server. And if I am a client, I can open the device and generate a magic number which I will send to the server, which will then use this number to authenticate me, and I will be able to render. But there is a recent other way introduced, which is render nodes. So render nodes are device paths that I can open the device with them and render without the need of authentication. But since I don't need any authentication, I won't be able to do some functionalities like gem names. So what are gem names? So to share the buffers between different contexts or devices, there are several ways. First, you may know that the devices, for example, if you have a dedicated card, it has its own memory. It's VRAM. So it's only for your device, but in RAM, you can share memory between all the graphic cards because all the graphic cards can have access to the RAM. To share the buffers, you have to give a meaning to the buffers. So when you manipulate buffers in your driver, you will manipulate handles, which are numbers. And this number will only have a meaning for you, and for you will be a buffer. For example, Mesa uses handles. But if you want to another context to use your name, you can your handle. You can generate a gem name. A gem name is a global handle for the device, which means that everyone with this number will be able to access to this buffer. But it's insecure because if you try and guess the correct number, you can access to the buffer. And since the numbers start from 1 and are not very random, then it's easy to catch some buffers, and so it's very insecure. And DRI2 use them because it was the only technology available at that time to share buffers. But now we have also prime DMA file descriptors, which describes what the buffer is and where it lies in memory and gives the right to access it. So it's secure because you can't guess all this information, and to open a file you have specific rights, so it's very secure. And we will use it by default with Wayland, and there are 3 use only them. Now about memory speed. So rendering to RAM is fast if you have a direct channel to talk to them. For example, for VRAM DDR3 with a frequency of 900 megahertz and 128 bits for the channel, you have a high capacity to read and write, so about 14 gigabytes per second. So that's fast. But if you have to use a channel to access to this memory, for example, the PCI Express channel, so I took the example of the channel that is on my computer. And so I have 8 lanes of 500 megahertz bus. And so that means per second I can share 4 gigabytes via this bus. If I had an external device with Thunderbolt, it would be only 1 gigabyte per second. So that's much slower than direct access to RAM. So how can that have a meaning for GPU offloading? Well, a full screen, full HD buffer is about 8 megabytes, but if I have to share 60 frames per second, it's going to be a little more, which is about 500 megabytes per second. So let's do a test on my system, which has an Intel card and an AMD card. Both have their own memory access, but the AMD card, to talk to RAM, has to go through the PCI Express channel. And if I render a very, very light test, which doesn't give any indication on the performance of the graphic card, but only on the speed of the memory. If I say, well, render this test in RAM, the Intel card, which has fast access to this RAM, will be about 10 gigabytes per second. So it's near what we saw before, which was 14 gigabytes per second, the maximum. So there is a bit of rendering, so that's why we don't access the maximum number. But for the AMD card, we saw only 5 times less frames, because it is limited by the PCI Express channel. So likely, since your application will be not light but heavy, it will use the PCI Express channel to communicate input and data. So with GPU offloading, when you want to use this card to render, you shouldn't expect to have high FPS like this. Now about tiling, you may have heard of it. Tiling is a way of reordering the pixels in memory so that your graphic card will render faster with this tiling. It's very good for performance. For example, on my Intel card, which tiling has a big performance impact. With OpenArena, I get 3 times more FPS frame per second with tiling. So that's a huge difference, but for some application, it won't have any difference. But the big problem about tiling is that we can't give a buffer to another card and say, okay, read it if it has tiling, because the other card won't understand anything. In fact, it depends on the models and the things of the card. So for example, here's Western Gears rendered on my AMD card, and the Intel card is displaying. So I say it shouldn't use tiling, so okay, the Intel card understands. And here it's when I allow the AMD card to use tiling. So we see that, for example, the green pixels are much more in line than before, where it was a GIR. So we can understand that it's faster to manipulate like that, but we would like this to be shown properly. So when we'll have to deal with tiling, what we want is we want to combine the high performance of tiling and the fact that we need to share a linear buffer with the card. So what we want to do is to render to a tile buffer and then do a copy to a linear buffer. When I mean linear, I mean with no tiling. And to finish with DMA buff fancies, which when you share a DMA buff, which is what we do to share the buffer between the two cards, there are no fancies shared between the two devices, which I mean internally each card has its own fancies to say, I have not finished yet to write on this buffer, wait a bit before reading it. And all this works pretty well, but with 2 different devices, they won't share these fancies. So they will show garbage. And hopefully a new solution will come, which is done by Martin Lankhorst, which are DMA buff fancies, which are shared fancies for all the devices. And this will remove glitches because the 2 cards will share these fancies and will do things correctly. An extra feature that has nothing to do with GPU offloading is that we can poll a DMA buff to know if the fancies are still there or not, which means that in user space you can know if the rendering has been finished or not, which is cool. Now, how does GPU offloading work with X DRI2? So the main mechanisms to render with X DRI2 is I'm a client. I tell to the X server, hey, I want to render. And there is a special bit to say I want to render on a specific device, not the main one, perhaps. And then the X server will give back a path. We open the device at the file at this path, which is the device. And then we have to authenticate, generate a magic number, send it to the X server. Okay, then in the DRI2 scheme, I have to ask the X server my buffers, which I will use to render. So I will ask, yeah, I want a buffer. Okay, the X server gives a gem names. So remember that it is insecure. And the client will use these gem names to get the buffer and render to it. When it has finished rendering, it will tell the X server it has finished. It will swap, and X will copy the buffer to the current location. And if you have heard about the additional copies with compositing, it's here. When you do compositing, you won't allow the X server to copy directly to the screen content. Instead, the X server will have to copy to an intermediate location, and then the compositor will then copy what it is at this intermediate location to the screen. So it's two copies, whereas we could use only one. And Wayland and DRI2 improve this, and we have only one copy. Okay, so how it works with GPU offloading. First, you have some configuration to do. You have to provide a specific driver for each device. DDX is a driver specific to load X with the device. And both have to be loaded at the start. You can either write what you want for DDX to be loaded for each driver in exoc.conf configuration file, or it's automatic if you don't have any exoc.conf configuration file. And next, once the computer is started, you have to use xrender to say what you want to do with these devices. You have two modes. The one used, for example, with NVIDIA proprietary driver is to have one GPU for display, for example, the Intel card, and one GPU for rendering, for example, the NVIDIA card. So it's not GPU offloading exactly. The second one is GPU offloading. You have one GPU for display and rendering, and the other one can be used eventually when you want by specifying specifically where you want to use it. So here you will have to configure this mode. Each device will have a provider number, and you can specify which provider number will be for displaying and which for offloading. And with DRI prime, you can say provider 1, I want to use this provider for rendering, and often 0 is for the one displaying, and 1 is for the one the second one. So that's why you use DRI prime equal 1 always when you want to use the secondary device. So internally, how does it work? In the X server, it has loaded the correct DDX for you and send you a correct gem names on your device. But when you will commit the buffer, the location of the X server, when it does the copy, will have to be shared between the two cards. So for that, it will use the prime DMA buffer API, and it will have special codes in the DDXs to handle that and create a linear buffer, so with no tiling, shared between the two cards. So this will require special code in the DDX and X server to handle all that. When you don't have compositing and the client is full screen, the target will be directly the full screen Canoe buffer. There will be an exchange so that it is possible. But if you don't have compositing and your application is not full screen, you will see nothing. It will be a black surface just because there is no one who cares about the copy to the linear buffer shared to the screen pix map. But when you have compositing, it is done, so it works. And to make glitches, to remove glitches, every time the buffer, we say that a part of the buffer has been rendered again, we say no, the whole buffer has to be loaded. And it works, but with T-rings. So T-rings is, I'm displaying a frame and I write over the frame whereas I'm displaying. So I have new and old content on the same frame. It's very strange, and It doesn't look nice. There is no synchronization at all with screen refresh. But at least the content is correct because you always copy to a buffer whose previous content was correct but old. Then even if you read before it has been finished writing, you will see the correct thing. Because as you remember, there is no fence shared between the two devices. So one will write on the buffer and the other will read at the same time. So that's also the root of the tearings. We can't do without tearings in this situation. So how can we make that work with Wayland? So in Wayland, the main mechanism is that the client is aware of the path of the device path of the compositor. The compositor says, I use this card, and you can connect to it. I can authenticate you to it if you want. But the client could also open another device and especially use the random node of the device and then doesn't need authentication to the compositor. And the rendering is a bit different because it doesn't ask any buffer to the server, like for DRI2. It will have its own set of buffers, will make the server aware of these buffers, so it will import them, and okay, I know these buffers. And the client will choose one, render, and then will send to the compositor, and the compositor will use it. The client will render to another buffer, and the compositor eventually, when it gets a new web buffer, will release the old one and say you can reuse this buffer again. Okay, so how can we make GPU offloading with that? Obviously, we can choose the device we want to render to. What we want to improve first over DRI2, we want to remove the tearings. It would be cool, right? But we want some synchronization. So it's possible with Wayland because we have a way to synchronize to the refreshes of the compositor without actually care about the GPU. It's a sort of frame callbacks. And it would like to have the least possible code in the server, so everything should be client side. So it's possible since the client knows the device of the compositor, it can actually knows, well, I will give to the compositor a buffer it can understand. So that makes sense. And we would like some sort of hot plug support, and that's all. So the very first scheme that came to mind, which is not very good, is that the server will be the DRAM master of all the cards and will advertise all of them. I can authenticate to them, okay? And the client will see, oh, I have all these sets of buffer of a device I can use. I will choose one. And then the client will send a buffer the compositor can read with no tailing. But there is still some issues with this approach. We have still server-side code to be the DRAM master of all the devices, and we want to simplify that. So we say that we will rely only on random nodes. The compositor won't do anything, won't have new codes. We don't change anything to the compositor, and it will everything will be client-side. It will use random nodes, and no need of extra code. So everything is in the client. But remember, for X DRI2, we had a way to specify which device we want to use. We had a provider number, which was mostly constant because it was 0 for the one displaying and 1 for the other card. So here we have to find something else. The device path of the device is not constant across reboot or across updates because it depends on the speed of the boot of the driver. So we decided to rely on a tag filled by UDEV, which doesn't change attribute and which looks like that. So this is the ID path tag for my dedicated card. And when I want to use this card to render, for example, GLMark2, I will use this command. But since it's a bit tricky to remember all that. We decided that one will be a special meaning to say that I want another card than the compositor. So when you have only 2 cards, it takes the other one. So it will work, but in Wayland you can launch embedded compositors, and you can launch client inside this compositor. And here we would like to be able to launch clients inside the compositor on the dedicated card if we want. And so if I do this and launch an embedded compositor, all the clients will use a different device than their compositor, which is the embedded compositor. So we are not using the device we want. They will all be using the Intel card instead of the AMD card here. So here will be the sure way. You are sure what device will be used. And here it's the different card than the compositor. OK, so hotplug can be supported because there is no server-side code to detect there is a new device and do something with it. So that's cool. But as we said, we are going to share a linear buffer with the compositor when we don't use the same card than the compositor. So it isn't optimal to render to this buffer. And we said that we want to render to a tile buffer and do a copy to a linear buffer. So how can we do that? And there are 2 ways. The first way is say, well, compositing, it's light. We can do compositing to a linear buffer. So when I would like Okay, so there are 2 possible ways. So the first one is to launch an embedded compositor on the dedicated card, and all clients inside will only know that their compositor use the dedicated card, and will use tiling because they know they can share tiling buffers with their compositor. But the problem with that approach that we induce some lag because there is an extra layer. There is more CPU consumption, and so it's not kind of cool. But remember that, okay, it's working again. Remember that we had, that I'd say that with DRI2 it was cool that the content was okay even if Francis didn't work. So here we'll have this problem because we give fully rendered buffer to the compositor, and it won't be copies of already correct buffers. And so if you directly show the buffer, it will be semi-black or it will not show the correct content. So you have to have a small lag so that the rendering finishes. And so right now, only this solution will give correct content. Because the second way is to say, well, do the copy in Mesa and send the copied buffer. But we have glitches with this approach because we send a buffer that is not finished rendering, and the compositor will just read the black content. But when we do the copy, we can say, well, I will wait before committing that the rendering has been finished. So it's equivalent to GL finish. But it is very slow. It's severely impact performance because when you have finished renting and you send the buffer, then there will be a long time before you feed new rendering commands to the graphic cards, so it won't be used fully. That's why it decreases performance. But the good thing is that in both cases you can run a full desktop on the card you want. For example, if I launch a full screen nested compositor, it will just work. There will be a small lag, but all my desktop will be rendered on the dedicated card. It is a full screen buffer, so the Intel card won't have anything to do than displaying. Also, the 2 approaches have no tearings, even if they can be glitches. And the synchronization to the screen refresh is working. So obviously, the second way here the copy in Mesa is what we want to do for most of applications, but it will have to wait the enable fancies to be fully workable. Okay, now I want you to think about another case, which is I have two cards, but also two displays, and each of them is connected to one of the cards. How do we want to handle that? And that can happen on some laptops where the VGA connector is on the NVIDIA card. And on Windows, in this case, what they do is that they switch so that all the applications are rendered on the most powerful card, which is the dedicated card. But first, we don't know how to switch GPU online with our technology in Mesa and the kernel. Maybe one day, but I think it's very far. So what we want to have is a compromise, I think. I think we want that each client created on one display will be on the device connected to the display. It's possible. So I have two displays, and each client will use one of the graphic cards. They will be able to use styling, etc., have good performance. But if I want to change off-screen one application, since it's on the other card, I will have to do something. So this will have to be handled by the compositor. The compositor will have to have two Wayland connections for each display and display both in one for one display and one for the other. One will connect to the dedicated card and one other for the integrated card. And when it knows a client wants to change off screen, it will have to do a copy. So it's not perfect, but at least if you launch the client of the display you want, you will have the best performance possible because you can use styling, page flips, etc. without endless copies. Okay, so I will repeat a bit and summarize. For X DRI2, the server controls the devices. It is their master of them. It has special code to handle them. And there is a DDX for each device. The copy type buffer to the linear buffer is handled in the X server. The client doesn't do anything. And there is special logic for that in the DDX. The clients always authenticate to the server. And obviously, the DDX has special code to handle that. With Wayland, we don't have any code in the server, except for the last example I told you, but this isn't a feature working in X2. And we rely only on random nodes. The client knows it uses a different device than the compositor and adapts itself to have it has special code to handle that and rendered to a tile buffer and copy to a linear buffer. And it can be with an embedded compositor eventually. So right now, what has been done so that the perfect GPU offloading support is there? So random nodes are here, and they are going to be defaulted soon. Right now, you have to have a special command line when booting the kernel to have random nodes. The patches for using DRI prime in Mesa to indicate what device we want to use with ID path tag, it's working. And also a cool feature with recent kernels is that the GPU you don't use can shut down when unneeded. So you don't have to do it manually, it's good. What needs to be done is DMA fancies. As I said, it's most wanted features. We need also to handle the copy in Mesa, but once DMA fancies are coming, I think we will add it pretty soon. Also, instead of using DRI prime to indicate what device we want to use for a program, we don't want to use scripts and so ideally we want something automatic, which I would say I want for this program always to use device A, for example. And DRI conf, which is already used to customize the parameters of the graphic cards for several programs, can be used for that. So there has been some work on it, but not finished. Also, some remaining applications are still relying on gem names, even Wayland applications. Like VA API, it's still using an old Wayland interface when there was no DMABF support yet, so it has to be rewritten, but it's not so much work. And obviously, the compositor has to do some special things to handle multiple displays connected to different devices. But I think it will be very cool. Now, how it can work with Wayland. So I don't know if you know about Wayland. So basically, it's an X server connected to the compositor, with a Wayland compositor, and it tells the new clients that come up, and Wayland will send the buffers correctly. Glamour is what we want to use for GPU acceleration. It's a library based on OpenGL that handles X render, because X can do some acceleration from the clients, but Wayland not. And since it's OpenGL based, we don't have specific GPU code for all the cards, so it's all in Mesa. And if you think of it, we don't have a real need to support X GPU offloading like it is supported with DRI2, because we can already launch an embedded compositor on the card we want, and inside all X application will run on the card of the compositor. So we can already have GPU offloading without supporting X GPU offloading and have several DDXs. So what we want is to have only one DDXs loaded for Wayland. Okay, but there is some problems. DRI2 doesn't work with random nodes, obviously because it uses gem names which are forbidden on random nodes. So we have to support DRI3 only for this use case. And DRI3 work with random nodes because the difference is you don't get the device path you want to the server to use. You ask an already opened file descriptor on the device. So the server can do whatever it wants and use random nodes, etc. And DRI3 use only DMABF FD, which are supported by random nodes and are secure. But DRI3 is not entirely ready. It's still under fixing, but I think it will be ready for production soon. So do you have any question? Yes? Maybe someone can give a micro for the questions?
It's coming.
Yes.
It's coming. Where's the... Oh. Thank you. It's good, it's good. Yeah, yeah. At least, it's on. It's red, but... Okay, this one's right too. Maybe you can repeat my question after I said it.
Okay.
For the video. So, macOS has the option that if you move a window from one GPU to another, actually one screen attached to one GPU to the screen or multi, to send a notification to the application so it restarts its OpenGL rendering. So you don't have to copy around the data all the time. Did you think about something like that?
Okay, so the question is about with macOS, they have an option. They can, when we move, we have two displays connected to different GPUs. We can have application on one display connected to the right GPU, but when we move the display, notification is sent to the application so it can change of device. So can we have a similar support? Well, I was told there was an extension, but I think it's only GLX, I'm not sure, when we can say to the application that OpenGL is broken and it has to redo everything from the start. So it could be used to do that, but I was told that no application care about that, so so obviously it will be some application support.
Well, we need some dual monitor setups of different GPUs working first. So
Yes. But since since they would have to do all the work again to initialize, they will need special code in the client to handle that. So if it's not an initial extension, it could be added eventually to the Wayland protocol, or I don't know. We can find a way, but maybe later. Is there other questions? Here? Yeah, in mono micro.
For the copy after the offload GPU has written to its tile render buffer, is on the NVIDIA side of that render, that tile format is the document sufficiently for you to use Wayland to deswizzle it as you copy it to the front buffer, to the screen?
So your question is, when you do the copy from the tile buffer to the linear buffer, do we have enough information to convert the tiling when we do the copy? Is that your question?
To avoid the extra blit.
Yes. To avoid the blit, it is understanding the tiling directly. Unfortunately, this would need support for the tiling for the cart itself. So it's not possible, unfortunately. We need a copy for that. There is no other way. Other questions? Don't be shy. Thank you. Thank you.
Guys, when you're leaving, can you help us out a bit? All the trash is there, take it out. Even if it's not yours, take it out. That saves us a lot of time.
Oops.